In the last module, we had just completed principle of similarity, and we had identified, we non-dimensionalized the momentum and the energy equation. When we non-dimensionalized the momentum equation, we got Reynolds number. When we non-dimensionalized the energy equation, we got Reynolds number, Prandtl number and Eckert number. So, here this we saw that, coming back to my slides, we saw that the Reynolds number is the ratio of inertia force to the viscous force, and Prandtl number states how much momentum diffusion is greater than or lower than in comparison with thermal diffusion. For example, if Prandtl number is less than 1, momentum diffusion will be less than the thermal diffusion. Okay, this, let us remind this, we will come back to this again when we are going into the scale analysis. So, Eckert number is how much of the kinetic energy gets transformed into thermal energy. So, as I said, it is important only for supersonic or hypersonic flows. So, especially for space shuttles and high speed flows, high speed aerodynamic flows, we need to take Eckert number into account. But for subsonic flows, we said that Eckert number is very small, 0.01. So, we will have only the Reynolds number and the Prandtl number as our non-dimensional numbers which are important. So, now what we are going to do is, very interesting thing is that we are going to study, before we do that, let us just remind ourselves the Nusselt number. This dimensional similarity was actually done by, over to the slides, the dimensional similarity was done by actually Professor Nusselt. So, he did his doctoral thesis on conductivity of insulating materials. He became professor after he worked on heat and momentum transfer in tubes. He did this non-dimensionalization what we did just in the previous module, that is what is called similarity theory of heat transfer. He was responsible for that. Of course, he has done film condensation, what we call as Nusselt condensation, and he was professor in University of Karl Lewis and professor at University of München, and he was he worked till the age of 70 and lived for 75 years, and he passed away in 1957. He is quite contemporary that way. So, then we will move on to the next similarity, that is scale analysis. Let us move on to scale analysis. So, the objective of this lecture or this module is that we will try to recap conservation of mass, momentum and energy, state the outcomes of these equations for an engineer, reduce these equations for two-dimensional steady incompressible flow, and we will do scale analysis of the momentum equation to get the hydrodynamic boundary layer thickness and skin friction coefficient, and we will further do scale analysis of energy equation for Prandtl number less than 1 and greater than 1 to get the thermal boundary layer thickness and Nusselt number, and how do we extend this discussion for Prandtl number equal to 1, and we shall summarize the results and get the feel of all parameters what we have estimated. So, these are the governing equations which we had derived. I would not like to write all of them because we have derived this, and I just want to show you these equations. This is the mass, conservation of mass, x momentum equation, y momentum equation, z momentum equation and the energy equation. Now, if I take the momentum equation, what is that I am trying to do is, I will try to understand this and reduce this to the two-dimensional. We will write this for two-dimensional. So, let me write two-dimensional incompressible steady flows. Let me get back to slide. In this slide we have rho du by dt, that is nothing but my inertia force, minus del p by del x is the pressure force, mu del squared u by del x squared, del squared u by del y squared, all of this is the viscous force, plus Fx is the body force. Du by dt is the total derivative of my velocity, that is du by dt is equal to all of this. Now, if I solve this, if I solve this momentum equation, now let us say if I solve mass and momentum equation, if I solve mass and momentum equation, if I solve all these four, what is that I am going to get? U, V, W and P. Okay. What use it is for an engineer? He does not care about the velocities, he cares what does he want. He would be interested in hydrodynamic boundary layer thickness and the skin friction coefficient CFX. How? I will explain you just a little later. Delta is hydrodynamic boundary layer thickness and CFX is skin friction coefficient. Okay. Now, you see, I want to remind you, mass and momentum equation, when we non-dimensionalize, what was the non-dimensional number we got? We got Reynolds number. So, it is natural for us to expect that the delta would be a function of Reynolds number and CFX would be also a function of only Reynolds number. So, let us see how does that happen, that is delta as a function of Reynolds number and CFX as a function of Reynolds number. So, just to make you understand what is boundary layer thickness, because I have not introduced it, if I just take a flat plate, and let us assume that there is a free stream velocity which is flowing on this by a fan u infinity, that is like this paper is there, my paper is there, on this paper it is just flowing. Okay. Now, this is my x direction and this is my length. Okay. Now, x, y, u, v. Now, boundary layer thickness, we say that the boundary layer thickness grows like this and this is my boundary layer thickness. What is this boundary layer thickness? It is that thickness, that is the location of y at which u by u infinity is 0.99 times. That is, if I take a pitot tube and start measuring the velocity, that location at which my velocity is 0.99 times the u infinity, that is my boundary layer thickness. Here when I say boundary layer, I mean hydrodynamic boundary layer. So, what is CFX? CFX is equal to tau wall upon half rho u infinity squared. What is tau wall? That is nothing but wall shear stress. Okay. And rho is the density of the fluid and u infinity is the free stream velocity. Okay. Now, what is that engineer interested in? Engineer, how will he use this CFX? I said engineers use his CFX. How will he use? He would be interested in net force exerted by the stream on the plate, that is F equal to integral of tau wall, this tau wall is varying with x into W within the limits 0 to L, that is tau wall W dx 0 to L. So, what is W? W is the width of the plate. So, if this is my plate, this is the length across which the boundary layer is varying and this is the width of the plate. So, width of the plate. It is this engineering necessity, finding F is the engineering necessity. It is this engineering necessity drives us to find a tau wall, that is to get a tau wall I need to get UVW. Just to remind you, what is tau wall? Tau wall in this case for flat plate it would be mu into del u by del y, at y equal to 0. So, this is, so you need velocity gradients, that means you need velocity distributions. So, you need velocity distributions from which you will get shear stress, from which you will get Cfx, that if you, from where you get the tau wall, from tau wall if you integrate, you are going to get the net force exerted. This net force exerted by the stream on the plate, this is the engineering necessity. This engineering necessity is what drives us to solve the mass and the momentum equation. Similarly, if I will go back to my slides and just take a recap on energy equation. So, in the slides you see that conservation of energy, you have rho Cp dt dt which is the convection term, k del square T which is the conduction term, dP by dt is the pressure work, plus phi is the viscous dissipation term. So, now if similarly, now let me get back to writing. So, what is the outcome of the energy equation? If you solve energy equations, remember you have already solved and gotten u, v, w and p from momentum equations, and now if you solve the energy equation known. So, if you solve the energy equation, what is that you are going to get? Temperature. From the temperature you are going to get delta T and Nusselt number, delta T and Nusselt number. What is this delta T? Delta T is thermal boundary layer thickness. And what is Nu? Nu is the Nusselt number. So, Nusselt number is an engineering necessity. I will just show you in a little while from now why is this Nusselt number an engineering necessity. So, but I have not told what is hydrodynamic boundary layer thickness, but before I tell that, I just want to remind you what did we get when we non-dimensionalized the energy equation. When I non-dimensionalized the energy equation, I ended up for subsonic flows Reynolds number and Prandtl number and Eckert number. So, for subsonic flows, it is natural to expect that Nusselt number would be a function of Re and Pr, correct. Now, let me define, make you understand what is this thermal boundary layer thickness. So, let us say I take again a flat plate, and in this flat plate there is a free stream velocity which is flowing with velocity u infinity and whose temperature is T infinity, and I am maintaining this plate at a temperature Ts. T infinity can be greater than Ts or Ts can be greater than T infinity, it does not matter. One is heating the other. Now, in this situation, here I am taking Ts is greater than T infinity to show the thermal boundary layer thickness. So, you will find something like this, that is, here you will have T infinity, here you will have Ts. So, there is a location where my T infinity Ts minus T minus T infinity upon Ts minus T infinity is 0.99 times. So, it is that location of y where my temperature difference T minus T infinity is 0.99 times the Ts minus T infinity. So, this is thermal boundary layer thickness. Okay. So, now what is Nu? Nu is equal to HL by Kf. Kf is the thermal conductivity of the fluid, because it is in this thermal boundary layer conduction is happening. So, what is H? H is equal to minus K del T by del Y at Y equal to 0 upon Ts minus T infinity. If you recollect, in the very first module we have introduced the definition of H. So, this is H. So, H is the heat transfer coefficient, Kf is the thermal conductivity of the fluid, Ts is the surface temperature, T infinity is the free stream temperature. Now, what is the engineering necessity? Engineer is interested in resistance to the transfer of heat from plate, here Ts is higher than T infinity. So, from plate to the stream. What is this? Or you can simply say heat transfer rate, that is heat transfer rate Q dot equal to H into area, that is length into width of the plate into Ts minus T infinity. Engineer is interested in Q dot, he knows L and W, he knows Ts and T infinity. If you were to get H through a nu, which is a function of Reynolds number and Prandtl number, you will be able to compute the heat transfer rate. It is this engineering necessity to know Q dot drives us to get H, that is expressed in terms of Nusselt number, that comes only from temperature distribution and the velocity distributions. So, this is why we derived mass, momentum and energy equation. So, now what we are going to do in the next slides is that we will first consider laminar, we will write laminar boundary layer over a two-dimensional body. Okay. So, now what are the assumptions I am going to make are properties are constant, flow is incompressible, that is subsonic flows, then flow is steady, then laminar flow. I am considering laminar flow. Now, let me get back to my slides. If you see the conservation of mass, it is d rho by dt plus rho del dot V, and it is incompressible. So, d rho by dt would be 0, and there is no W, or the variations with W in Z are 0. So, there is no W. So, you get the continuity equation as del U by del X plus del V by del Y equal to 0. Now, I get back to my slides again. If you see conservation of momentum in the x direction, so you have rho del U by del T plus blah blah blah. So, here if you see here del U by del T is 0 because it is steady flow and there are no variations in Z and W is 0. So, therefore, W del U by del Z is 0, and so the left hand side I get U del U by del X plus V del U by del Y equal to. Now, again back to slides, the pressure term has to be there, that I cannot neglect. So, if I divide by rho, I will get minus 1 by rho del P by del X. Now, in the viscous terms, here you see del squared U by del Z squared would be 0 because there are no variations in Z. And now by continuity, we said that it is an incompressible fluid. So, this is nothing but del dot V. So, this would, whole of this term would be 0, and I am not considering any body force. So, Fx is 0. So, right hand side reduces to minus 1 by rho del P by del X plus nu del squared U by del X squared plus del squared U by del Y squared, del squared U by del Y squared. Now, let us take up Y momentum equation, again back to slides. So, you have del V by del T equal to 0 because steady flow, and W is 0. So, you on your left hand side you get U del V by del X plus V del V by del Y, and pressure term would be there. So, minus 1 by rho del P by del Y with the same arguments what I did earlier, that is del squared V by del Z squared would be 0, back to slides, del squared V by del Z squared would be 0, and by continuity equation whole of this term is 0 and plus Fy is 0. So, you have plus nu del squared V by del x squared plus del squared V by del y squared. Now, back to slides, conservation of momentum, z direction, W itself does not exist. So, whole of this equation is 0. Consider energy equation. So, here what is that? Rho Cp del T by del T for steady flow would be 0 and W is 0 and there are no variations in Z. So, you have W del T by del Z is 0 and again del squared T by del Z squared is 0 because there are no variations in Z, and dP by dt and phi term are 0 because we are considering subsonic flow. Why it is subsonic? Because flow is incompressible. For incompressible, it would be incompressible only for subsonic flows. So, the energy equation reduces to U del T by del x plus V del T by del y equal to alpha del squared T by del x squared plus del squared T by del y squared. Please notice I have divided K by rho Cp and written that as alpha. Now, what are the boundary conditions I have? At y equal to 0, u equal to 0 which we call as no slip, and v equal to 0 which we call as impermeability, and T equal to Ts, that is constant wall temperature, and at y tending to infinity at any x, u is u infinity free stream velocity I am taking, and uniform flow, this means that it is uniform flow, v is 0 and that is u equal to u infinity, v equal to 0, uniform flow and T equal to T infinity. So, this is what we have done. So, now what we shall do is we shall take up the next, we are going to take up with these equations, we will do scale analysis of mass and momentum equations. You see, if you recollect, we had found that, if you just see it here, if you recollect, if we solve mass momentum equations, I said that we can get delta and Cfx. We will not solve these equations, but we will, without solving the equations, we shall do the scale analysis and try to get delta and Cfx with using mass and momentum equations. So, how do we do that is, let's do that. So, let's draw the boundary layer. So, that is, I have a flat plate, I am considering a flat plate, and I have u infinity, I am considering mass and momentum only. So, I have boundary layer growing. Notice that boundary layer is growing, I have not explained why boundary layer is growing, that will come out from this analysis. So, this is delta, this is u infinity, this is u, and this is x. Okay. Remember, we had momentum, let us write those equations, that is del u by del x plus del v by del y equal to 0 we got, u del u by del x plus v del u by del y equal to minus 1 by rho del p by del x plus nu del squared u by del x squared plus del squared u by del y squared is what we got as the x momentum equation. Y momentum equation is u del v by del x plus v del v by del y equal to minus 1 by rho del p by del y plus nu del squared v by del x squared plus del squared v by del y squared. So, we shall do scale analysis. So, what is the scale analysis? What we say is that u scales down to u infinity, or it is of the order of u infinity, that is meters per second. Okay. See this, and then x is of the order of the length of the plate L, that is in meters. Now, y is of the order of boundary layer thickness delta, hydrodynamic boundary layer thickness, if I have to be very specific, that is of the order of mm. Why mm? We will understand, we will get the closed form solution, it would be of the order of mm. So, now let us try to find the order of v from continuity equation. If I take continuity equation, so what is that order I get? What is the order of del u by del x? It would be of the order of u infinity by L. See, it is del u by del x. It is like u infinity 1 minus u infinity 2 upon x1 minus x2. But I am taking it is of the order of u infinity upon L, and which should be of the order of that is I am writing tilde. Tilde represents order of. Okay. So, v upon delta y, y is delta. So, v is of the order of u infinity delta by L. Notice that I have not written equal to, I have written order of. So, if I have to write equal to, some constant has to come here. I do not know that constant, but I just know the order of. So, let me call this as equation 1, equation 1. Okay. So, now you have the x momentum equation, let me take and write the order of magnitudes of the x momentum equation. So, what is that you get? U infinity, and what is the order of del u by del x? U infinity by L, because delta x is L, comma v is of the order of u infinity delta by L, and del u by del y is of the order of u infinity by delta, is of the order of minus 1 by rho del p by del x. I do not know what to do with it. So, I am keeping as it is, that is I take it as if it is important, comma nu. What is the unit of del squared u by del x squared? Here usually students get confused. I would like to write del squared u by del x squared is meter per second squared, meter per second squared. Okay. Sorry, meter per second per meter squared, meter per second per meter squared. So, you have del squared u would be scaling to u infinity upon x squared would be scaling to L squared, nu u infinity upon L squared, comma nu del squared u by del y squared, nu u infinity, what is the scaling of y squared? Delta squared, that is delta squared. So, you have right hand side, if you see, you just see delta gets cancelled out. So, you get u infinity squared by L, both the terms, that means both are important, you cannot throw out any of them. So, the left hand side scales to u infinity squared by L, is of the order of, let me keep it as minus 1 by rho del p by del x. Now, remember delta by L is very much less than 1, because delta is less than L, delta is mm, L is meters. So, it can be imagined like 0.001, so which is very small. So, taking that clue, nu u infinity by L squared would be very less compared to nu u infinity by delta squared, because L squared is in the denominator. So, you can neglect this because delta by L is less than 1. So, you have on the right hand side nu, but you cannot throw out nu u infinity by delta squared, because delta squared is very small. So, let us write this as equation 2. Equation 2. Now, let me take up y momentum equation. So, we had written y momentum equation. So, let me rewrite that y momentum equation. U del v by del x plus v del v by del y equal to minus 1 by rho del p by del y plus nu del squared v by del x squared plus del squared v by del y squared. Let me recollect for you. U is of the order of u infinity, x is of the order of L, y is of the order of delta, v is of the order of u infinity delta by L. So, we shall do, what we shall do is, we shall do the scales of this in this and then try to find delta and Cfx. So, what is the answer expected? Delta has to be function of Reynolds number and Cfx has to be function of the Reynolds number. So much for this module. In the next module, we shall take this and get delta and Cfx from the scale analysis alone. Thank you.